Thanks to Brilliant for sponsoring this video. More about them at the end of the lesson. Today we'll learn to calculate the distance between a point and a segment. It's something we'll need during phase 2 of the self-driving car course starting next week. Like, if we want to know how far the car is from the side of the road, we need to get the distance from it to the nearest segment. We'll discover the math while coding a small interactive application that visualizes all the steps. To follow along, open the link in the description and get ready to go the distance. Get it? Because we're gonna calculate the... No.
Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now.
You'll already have a canvas initialized with the name myCanvas and some styles for it. And the page actually loads 2 scripts from my website. This is some vector math, so we're not going to reinvent the wheel. You can go to this link if you want to learn how those functions were implemented. I have links for them. And I also have links in this other file where I explain the drawing functions, but you don't really need to know those to follow along. We just use them to draw nice things. Now we're not going to need these anymore, so I'm going to close them. And let's begin by defining a point. A is going to be at 100, 200, and let's draw a dot at this location and give it the label A, like this. Save, and you should see this A dot appearing there at 100, 200. Let's add another point. I'm going to add now B at 400, 300, and draw it as well. And there it is. Now this is going to be the segment that we're going to calculate the distance to. So let's also draw this segment between AB like this. And we are going to calculate the distance from the mouse, this moving target here. So let's prepare a point for that as well. I'm going to initially define this M point at 250, 250, so in the middle of this line segment here. But we are going to add an event listener on the canvas for mouse move. And here we pass a callback function, and this one is going to change the X and Y location of M according to this offset. And now what we want to do is draw M, but actually clear the canvas and draw everything. So I'm going to make a function called redraw all, and this one is going to be here, like this. And first thing, it will clear everything. And now I'm just going to put inside of it all of these point drawings, like this. And the segment draw. And let's draw M as well at the mouse location. And now if you run this, you're not going to see anything unless you move the mouse into screen. So we have to call this redraw all once here in the beginning if we want the application to refresh and we can see M in the middle there, the default location. Now, it's very good to think about these points as vectors for what follows next. And I'm going to remind you a little bit about vectors. We usually draw them as arrows. So let's draw an arrow at A and copy this for B and M, the mouse point. And we get this. Vectors are drawn starting at the origin. That's by default when we define them as points like this. The other way to define them is using the angle and the magnitude, or how long the arrow should be. But by default, all vectors start at 0, 0. Now, let's start to write the code to project the point to the segment AB. And this function is going to first just get the difference B minus A. I'm going to store it in AB, and let's draw the arrow AB. And I want you to think, what will happen when I refresh next? Well, this is what we get. A new vector that would fit between A and B. Let me actually remove these other arrows now. They're a little bit annoying. So AB would fit there perfectly between A and B, but it's a vector, so it starts at the origin. We could draw it, we could apply it in any point in the space if we really want, and let's do that. I'm going to move this tail of the vector from there somewhere else. Let's define tail at 100, 100. And when drawing an arrow like this, we can pass a second parameter, and that would change tail from the default 0, 0 to whatever we pass here. So I want you to think, what will happen when we draw the arrow now? I will refresh. And we get this. Did you expect that the tip of the arrow is also going to change to preserve the orientation and length of the vector AB? Well, it doesn't, because it's still the same. We haven't changed that, just the tail. If we do want to translate the whole vector, then we have to change this AB by adding the tail there as well. So instead of AB, we add AB to the tail here, like this. And this is what we get. We could actually draw the tail here as well, consider it a vector as well, because it is. And now maybe things are a little bit clearer. So the arrow that was first drawn from the origin has now been offset by that tail vector, and it's drawn a little bit downwards and to the right. We could replace tail entirely here, just remove it and use A if we want. And what will happen now is the arrow will completely overlap with our segment. It's kind of not so well visible, but you can see the tip there pointing at B. The AB vector that we calculated didn't change at all when we did these drawing tricks here to make it look like what we understand when we work with vectors. So keep that in mind. This still is centered at the origin. Now let's get similarly the vector pointing at M starting at A. Draw the arrow in the same way so that we see it's centered at A. It's more intuitive in that way. And now we have this, an arrow that moves according to the mouse. And let's calculate something called the dot product. I will store it in this t variable, the dot product between vectors AM and AB. And let's draw this as text. This is not a vector, it's just a number. It's a simple number. And when we refresh, it's going to appear here in the top left corner. And we can see some values there. Some very big values when the mouse goes here, and even negative values on this side. Now, if you look at the formula for the dot product, it makes sense to get these very big values there because we are multiplying on x and on y, and then we are adding those values up. So we're going to get some big values. And it's kind of hard to make sense of them. But it's easier to make sense of them if we normalize these vectors. So if we type here instead of am, ab, n am, n ab, and define NAB as normalize AB and NAM normalize AM. And if you don't remember what normalize does, I'll show you by drawing NAM, again centered at A for consistency. Now, the arrow that I drew now is so small that you can't really see it except for the tip. Normalizing a vector means we are scaling it by the inverse of its magnitude, of its length. So we get a vector that is always of length 1, no matter the orientation here. So it preserves the orientation of AM, but not the distance. So it doesn't matter at all if I change the distance from A to M. It's just going to change the direction so it matches that. And we normalized both of them, AB also, but I'm not drawing the NAB because I don't want it to overlap that arrow and become confusing here. But look at this number now. It's between -1 and 1, and it's 1 when we follow AB directly. It's 0, very close to 0 because I can't do this perfectly, but it's 0 when these are perpendicular, and -1 when it's in opposite direction, so going from B to A. Now these numbers are a little bit more meaningful, but we notice that changing M closer to B like this doesn't change the result. It's basically a way to represent the angle here. 1 if it's the same angle as AB, -1 if it's the opposite, 0 if it's perpendicular. It relates to the angle in some way. But look what happens if we use AM here instead. So we keep AB normalized, but we don't need NAM anymore. Actually, we can remove this. So now, when I move towards B, if I move at B, that number there is actually the length from A to B, the length of the segment AB. And when I'm going shorter, it gets close to 0. And the other direction is with a negative sign, but basically the length of this AM segment is now written there if M is on the line here. Notice that if I move M away from this line, I'm going to move it away, but still somehow perpendicular to the line as well as I can, that number doesn't change. Or it changes a little because I can't do it well. But that number is not the length AM, it's actually the distance from A to a point P, which is the projection of M on this AB line. And if we go here and divide this value by the distance between A and B, then that number becomes again a value between 0 and 1, and then negative here. But unlike what we had previously, this number does increase if we change like this. So let's try to do linear interpolation with this value. And I'm going to go here and define a new point P. as lerp 2D between A, B using T. I have a video on this linear interpolation, so check it out if you don't know what it does. But basically, it gets a point between A and B T% away from A. And then we can draw the dot called P like this. And you'll see that we nearly solved the problem. P is actually at that location that we can use to calculate the distance from M to the segment. MP is the distance from AB, at least as long as the projection is between A and B, because it can also lie here outside the segment. In this case, that number on the top left is above 1. This is called extrapolation. And here we get minus values there. In this case, MP is not the distance from M to the segment. It should be MA, but we did solve part of the problem. And now this lerp here, I just wanted to show that we can solve the problem using it, but we don't need to use it necessarily. Typically, the formula when projecting a point just calculates a scalar here in the same way that we had previously. So only this part from here. It doesn't divide by this distance or magnitude of AB. And now this scalar is used to scale NAB directly. So an alternative way of writing P here without using the linear interpolation is just to add to A scaling NAB by this scalar like that. And you'll see that P is still in the same place. It's just another way to define this. But T is still useful, even though we're not using it here, because it tells us if MP is the distance to the segment or not. If T is between 0 and 1, then it is. If it's not, we have to do some other logic. But P is always going to be the projected point on the line defined by AB. So even outside of that, and this function is okay. Let's refactor it a little bit and remove these drawing elements. They were just for debugging here. And return here the two important things, P and also this T that we can use in future logic. Now here we are going to assign P and T to some local variables, and let's still draw P here so we don't lose it. But I removed those arrows that we had previously, so the interface is simpler now. Now, as I mentioned, the logic here is going to be if this T is between 0 and 1, then we know the distance. I'm going to draw it there as a text. The distance is going to be the distance from M to P. Let's also draw an arrow from M to P in this case. And save, refresh, and you can see now the same thing that we had before, but when P is not there, we don't have the distance anymore. That's the missing logic. So we're going to do that missing logic here in an else. We just have to take the distance from MA or MB, depending which one is smaller. So distance to A is going to be distance from M to A, and then distance to B is going to be distance from M to B. And now we do an if the distance to A is less than distance to B, we are going to draw the text distance to A. And let's also draw an arrow pointing at A to make it clear. And else we do the same thing with distance to B and an arrow pointing at B from M to make it clear. And now you can see that arrow points always to the nearest point on the segment, whether it's somewhere inside the segment or the segment endpoints themselves. Let's refactor this code and make our actual distance function distance from point to segment MAB. And I'm going to copy all of the code from here. So everything from this redraw all. We first have to project the point, and then I don't need to do any of these drawings here. Let's remove all these arrows. They were just for debugging. And here, in this case, we can return this distance. So I'm going to say return. And if we want to have the point where the projection happened as well, we can hold it here. And then the value is going to be just a distance. Let's wrap this properly. And I'm going to do the same thing here. So returning point A in this case, and the value distance to A, like this. And here, return point B, and the value distance to B, like this. Now let's use this function here above. And I'm going to take the result of this function into a local variable. And now we could draw, for debugging purposes, the text and also an arrow to the point starting at M. And let's save this. And now we get this final result here. Let's test also different locations for A and B. Maybe there's something special about this configuration and our code wouldn't work otherwise. So I'm going to go up here and copy this code and add another event listener for click. And clicking is going to change the location of A, like this. And now, if I'm going to go and click here, you can see top left corner value is 0 because M is now perfectly over A where I just clicked. And seems to work just fine. We can make a similar thing and change the location of B with the right click. Let's copy this one more time. We have to type here context menu. It's the event listener for when the context menu appears. And in that case, I'm going to put here B. And let's also not make the context menu appear. Otherwise, it's quite annoying. Let's test. And left click moves A, right click moves B. Do you like learning math interactively like this? A free and easy way is with Brilliant, the sponsor of this video. Brilliant is a website and app that teaches math, computer science, and other STEM concepts in a visual and highly interactive way. I really like their math explainers. They're really fun, and Brilliant customizes the content to fit your skill level, so you can solve at your own pace. My self-driving car course restarts next week. And to prepare for that, I really recommend their Geometry 1 course. From angles to triangles to polygons, Brilliant has you covered. We'd use most of the things there in our future lessons, so if interested, go to brilliant.org/Radu. You'll get to try Brilliant for free for 30 days, and the first 200 people to sign up will also get 20% off an annual premium subscription. Thanks for listening, and see you guys.